Hi there, welcome back. I'm Amy Jensen. Today we're going to do a quick review of characteristics of polynomials from a graph. So we're going to cover all of these characteristics and cover two different problems to do a little bit of a review to get you ready for your next quiz or test. So if you're confused and don't get it, hang in there, grab a piece of paper and a pencil, and let's get started. So we're going to start with this problem, and we'll do this one together, and then we'll follow it up with one that you can do by yourself and then check the answers. So here we go. In a typical problem like this, we are given a graph, and in this case, several of the key coordinate points are identified for us on the graph to make it a little bit easier for us to read. And we are asked to identify all of the different characteristics of this graph that are listed here. If you aren't sure what these characteristics mean, pause the video and go back, and you can scroll through the definitions that we showed at the beginning of the video. All right, let's get started. So let's start with the domain, all the possible x values. So the domain, recall, are all the possible x values that I can use as input into my function. In this case, there are no restrictions. It's all real numbers. So I'm writing that as negative infinity to positive infinity using interval notation. So that's the left side of the graph to the right side of the graph. The range is the set of y values that I can have in my function. And remember, the y values, I want to look from the bottom of the graph at negative infinity up to the top of the graph at positive infinity. So the lowest point on my graph is this negative 3.124. So the lowest possible value I can have is negative 3.124. And that's going to be a square bracket because it includes that value. And then it continues all the way up the graph to positive infinity. So we could work all of these things in order, but sometimes it makes sense to say, well, what's related to that range value, that negative 3.124? Well, that's the lowest point on my graph. So that's actually going to be my absolute minimum. This graph is going to have an absolute minimum at that same value, negative 3.124. And then since the graph continues forever in the positive direction, there's no absolute maximum. All right, so the range and your absolute max or min will always be related. And then remember, for the absolute values, we usually just give the y value, not the coordinate point. Now, if you gave the coordinate point for your answer, your teacher might not take off for that, but usually we just give the y value. Okay, so then let's go back up to the zeros. So the zeros, those are the places where, let's change colors here so we can see it better, where my graph is crossing the x-axis. So it's when it's asking for the zero, it's just the x value of my x-intercepts. So I have negative 2, negative 3, and positive 1. Now if I write those same zeros as an x-intercept, I need to write that as a coordinate point. So I'm going to have negative 2, 0, negative 3, 0, and 1, 0. And then likewise, the y-intercept, for the y-intercept, remember for that, I just want to plug in where x equals 0. So my y-intercept will always be 0, comma, something. And this point right here, 0, 6, is where the graph is crossing the y-axis. So that's my y-intercept. Okay, I'm going to come back to do increasing, decreasing, positive interval, and negative interval.
let me jump back down here to the relative maximum and the relative minimum. So a relative maximum is, we've already discussed that this graph does not have an absolute maximum because it continues forever in the positive direction. But if I look at this point right here, in that general area of the graph, that would be what we call a relative maximum. So it reaches a high point of the graph and then turns back around. So my relative maximum, I'm going to give the entire coordinate point here. So negative 0.681 and 8.645, I think it says. That's my relative maximum. Now my relative minimums would be the lower points on the graph. So I have a relative minimum right here, which is 1, 0. And I also want to include my absolute minimum in this point as well. So I have negative 2.569 and negative 3.124. So both of those would be considered relative minimums. Okay, so these values are going to come back into play when we look at the increasing, decreasing, and then positive interval and negative interval. So I'm going to look at the x values of my relative maximums and relative minimums, and that's going to tell me where my function is increasing and decreasing. So when I'm looking at my graph, I'm reading my graph left to right, and I'm looking at the x value. So I'm looking at my number line here from negative infinity over to where x is positive infinity. So if we look at the graph, I tend to just start with the graph on the left, and I say, okay, I'm going to start at the leftmost point, and my graph is decreasing from x equals negative infinity all the way until I get down to this turning point at x is negative 2.569, which you'll see is also my relative minimum x value right here. So it's decreasing from negative infinity to negative 2.569, and then it is decreasing again from the x value of that negative 0.681 until I get to the x value down here at the relative minimum to 1. That's where the slope of the graph is negative. You can look at it that way. Or if you were to be like a little bug on this roller coaster and you started way over here on the left, you go down the hill, get down to this where x is negative 2.569, then you start going up the hill until you get to x is negative 0.681, and then down the hill again till x equals 1, and then back up the hill for infinity. So the increasing values, again, I'm doing my x values. So my x values, where the graph is increasing, it's going to be the same value as this, and it's increasing until I get to my relative maximum right here of negative 0.681. That value right there. And then it's going to start increasing again. I didn't give myself enough space here. When x is 1 until we get to positive infinity. Okay, so these refer to, you can think of this as the slope of the graph. All right, so then the positive interval and the negative interval, this is where y is positive. So this is where my y values are greater than 0, and where it's negative, where y is less than 0. So anything that's above the x value is positive. the function is positive. Anything that's below the x-axis is negative. So for these, I'm looking at my zeros. That's what's going to show me where the graph is positive and negative. So if you want, take your hand and just cover up the portion of the graph that's below the x-axis. Okay, so when I'm going to write this in interval notation, again, I'm using my x values. And actually, this graph was the points that are showing up here as my x-intercepts. Really, just so we don't confuse ourselves, I should probably write these in the correct order. So -3, of course, is my furthest left is 0. So -3, -2, 1. And then we won't get screwed up on our positive intervals. So, okay, our graph is positive then, where x is -infinity until it reaches the first 0, -3, union, and then it's positive again from -2 until it gets to 1, union, and then 1 to infinity. So you might say, well, why didn't I just go all the way from this point at -2, 0, all the way to positive infinity? Well, technically, at this point, 1, 0, where the graph bounces right there, x equals 1 turns around and goes to be more positive. Technically, when it's on the x-axis, the function is neither positive nor negative. So you need to skip the value of x equals 1, because at 1, it's neither positive nor negative. So we use that union symbol and write it this way. Okay, and so then where is the graph negative? The graph is negative just between -3, x is -3, until x is -2. So it's important with the interval notation that you're writing it in the correct order, left to right. So again, these x values are a little bit confusing here because the -2, 0 is that one, and this -3, 0 is that one. It's just the way it printed on the graph makes it look a little bit confusing. Okay, so to wrap up this graph, the next concept, the function is even and odd or neither. This is talking about the symmetry of the graph. So if we're asked about the symmetry, this would be neither. It's neither even or odd. If we're asked about the exponent, the highest degree exponent, which is our next concept, the degree of the exponent, what we want to do here is count the number of terms and add 1. So 1 plus the number of terms. Our terms is anytime the graph changes direction. So we have 1 change of direction, 2, 3. So 1 plus 3, we get 4. So 4 would be the least degree of this polynomial. And if we want to know about whether the least degree or the highest exponent is even or odd, in this case, the answer to that would be it has to be even, which of course x to the 4th is 4 is even. But we know that the least degree has to be even because the graph is pointing in the same direction. It has the same end behavior. So while we're talking about end behavior, let's go figure that out down here. So end behavior, as x goes to positive infinity, over here, f of x, or y, also goes to positive infinity. And as x goes toward the left side of the graph, negative infinity, y still goes to positive infinity. So anytime that the leading exponent, the highest degree exponent, is even, these will always go in the same direction. One other thing that we might be asked that we're not right here, but this is also a good time to ask, what is the sign of the leading coefficient. The sign of the leading coefficient, that's determined by what is happening on the rightmost side of the graph. So over here. So since the graph is pointing up on the right, the sign of the leading coefficient must be positive because it goes up on the right. If the graph were going down on the rightmost side, then the degree would be negative. But we weren't asked that, so we'll just add that as a little extra bonus there. Okay, and then last thing we need to talk about is multiplicity. So multiplicity, really that's referring to our zeros from back up here. So -3, -2, and 1. So we have our zeros. And then the multiplicity for each of those at -3, the function is crossing the x-axis. So that would give us a multiplicity of 1. Again, it's crossing the x-axis at -2 as well. So that's a multiplicity of 1. But here, where x is 1, see how the graph bounces there. So that would give us a multiplicity of 2. And so now we have completed all of the characteristics that we were asked to do for this graph here. And just to add on to this problem, you might be given some of these characteristics and asked to write a function. So they might give us, say, maybe the end behavior and the multiplicity, and say, okay, what could the function be? So this function, actually, that we graphed here is over here. That's our actual function in factored form. So you can see the x minus 1, quantity squared. That's how we get our multiplicity of x equals 1. We get that twice. X plus 3, that gives us a 0 of -3. That occurs one time. And then x equals -2 occurs one time. So that's how we would get this function. And all of the characteristics that we've discussed. So hopefully that's a good review of identifying the characteristics from a graph. Now let's go on to another problem, and we're going to let you try it and see how you do. So we just went over one problem together. Now why don't you take a look at this graph and pause the video and see if you can complete the table over here with the characteristics of the function looking at this graph. So pause the video, and then when you're ready, we'll come back and you can check all your answers. Okay, so here we go. The domain of our graph, those are our x values. So we have all real numbers. The range in this case is extending all the way to the negative values and all the way to the positive values. So our range is also all real numbers. And be sure when you're writing interval notation with all real numbers, you always use open brackets, never a closed bracket. All right, so the zeros, those are just the x values of our x-intercepts. So we have -2 and 1. And then when we write that as an x-intercept, we would have both of those points. The y-intercept is when we plug in 0 into our equation, or we look at the graph in this case where the graph is crossing the y-axis, so that's just 0, 2. And of course the x-intercepts, y-intercepts, remember those are coordinate points. Now where we're talking about where the function is increasing and decreasing, we're going to give interval notation for the x values. So the function is increasing from -infinity until we get to our point right here, so to -1. union, and then it's increasing again from x equals positive 1 until x gets to positive infinity. And where is it decreasing? It's decreasing where x is negative 1 to positive 1. Just here, right here on this little slope there. Okay, then our positive interval, remember positive intervals are going to correspond to the zeros here. So my graph, my y values are positive from negative 2, and again this is interval notation, so from negative 2 until I get to 1, union, and it's bouncing, my graph is bouncing there, so I have to say union 1 to positive infinity. And then where is the graph negative? The graph is negative down here, which would be negative infinity until I get to x equals negative 2. And remember, all of these should be open brackets. Okay, relative maximum. So I have a relative maximum at the point negative 1, 4. That's right here. My relative maximum. My relative minimum is this point right here. But I don't have an absolute maximum or an absolute minimum because the graph continues in toward negative infinity and also toward positive infinity. So for these, I just write none. Okay, and then here we're talking about symmetry. So is the function even, odd, or neither? Neither. And remember, for an even function, that would be an example of even symmetry. And odd has to go through the origin. Oops. So even, you can fold the graph. It has symmetry across the y-axis. Odd functions have symmetry across the origin. And if it's been shifted at all, or it has any bumps, or in this case it's kind of wicky-wacky, it would be neither. All right, and then the least degree. So again, remember the least degree, I count the number of turns and add 1. So I have a turn right here, 1, 2. So the degree, the least degree would be 3, which makes sense because the highest exponent is odd. Multiplicity, again, I need to kind of list these over here with the zeros. So I had my zeros at negative 2 and 1, and then the multiplicity, remember if it crosses the x-axis, so right here it goes right through, so if it crosses the x-axis, the multiplicity is 1. If it bounces, the multiplicity is 2. And then the end behavior, so as x goes to positive infinity, over here, y is also going toward positive infinity, up here. And as x goes toward negative infinity, y is going toward negative infinity. So remember this, the least degree of this exponent is odd, so we should expect these go in different directions. The other question we could be asked is, what is the sign of the leading coefficient? We didn't talk about that before, but the sign of the leading coefficient is positive because the graph goes up on the right. Okay. So there we go. How'd you do? This is actually the function for this graph. So you can see that 1 has a multiplicity of 2, it happens twice, and negative 2 occurs only once. That tells us it crosses. So there we go. Hopefully that was a great review, and you should be all set. If you can do that without any issues, I think you've got it. So good luck, and just take your time on these kinds of problems because there's lots of room for error. So just take your time and you'll do great. Have a great day. See you next time.